Welcome back to TikTok with Eric Mijukovsky. The name has stuck with us for at least 2 episodes. We'll see how long it goes. Today, I'd like to start off a series of podcasts and blog posts where I talk about what it's like to build a smartwatch in 2025. I really want to show that it's not that hard to do, especially if you have PebbleOS, which is the open sourced firmware that runs on Pebble watches. Hopefully the work that we're doing at Core Devices to build these new watches will help other folks build new smartwatches as well. Smartwatches are not and should not be one-size-fits-all devices. I really hope that the work that we're doing in the open sourcing of PebbleOS may spark someone else's imagination and enable them to build their dream smartwatch that fits their needs perfectly. A smartwatch is a system made up of 3 main components. You've got the watch hardware, the actual thing that you wear on your wrist. And then you've got the software that runs on the watch. We usually call this firmware or the watch operating system. And then the third component is the mobile application, the companion app. This is the iOS app or Android app that runs on your phone, connects to the watch, sends notifications, downloads watch faces, controls settings, that kind of thing. So I'm going to talk about how you need to build each part of this system in order to build a smartwatch. But as a quick aside, I want to show you some ancient history, some old hardware. So this is a box that actually says ancient history, and it's got some fun things that I've built over the years. If you were building electronics in the early 2010s, you may recognize this. This is a SparkFun Electronics box. And yeah, we all had stacks and stacks of these. So let's see what's inside. A whole pile of junk. We've got some, early Impulse. I think this is what we included. Oh, Impulse. I guess I should explain. This is the very first smartwatch that I worked on way back in the day. I think we started working on this in 2008. Only worked with BlackBerry. I plugged it in. I was trying to actually demonstrate it, but I plugged it in. None of the displays worked. So this is, it had a transparent plastic back, kind of hilarious. One button. I can't understand why I only put one button on it. Man, that was not the best call. Oh, I've got some. These are 3D prints. Before we even came to the final design for Impulse, we tested a few different designs. This would look pretty cool. Oh, so I've got on my wrist. This is a Pebble, an original Pebble that we launched on Kickstarter. My favorite color is red. And this is it. This is the one that we sold 85,000 watches on Kickstarter. I've got this is my favorite sport band. It's kind of very light silicon rubber band. Anyways, I take this watch to Burning Man every year, so it gets a bit dusty. But I've still got it. Works great. This is let's see what the date was when it was manufactured. 2013. Yeah. Wow. Anyways, let's see what else we got in here. So this is the circuit board for the Impulse watch, for this watch. I really wish they would turn on. I wonder if anyone in the comments has an old. You could see the name. So the first company, the company before it was called Pebble, was called Alerta. I named it that. I can't exactly remember why. I think it was because obviously it has the word alert in it. What else do we got? Oh, we got a Pebble core. One of the only Pebble cores. This was funny. This is a Kickstarter, a failed Kickstarter that me and some friends worked on, where we built an iPhone case that would hold your AirPods. What else do we got? Oh, this is the first prototype for Impulse that I made myself. This is the extent of my hardware engineering capabilities. called the Watchduino, which had an Arduino chipset and a screen from a Nokia 3310 smartphone. Yeah, some good stuff in here. Oh, this is the this is the prototype that we used to record the first Kickstarter video. So we hadn't actually made the watch yet. I can switch back to the screen. So we hadn't actually made the watch yet. So what we did was we 3D printed a case. We didn't have a circuit board that would actually power the watch on. So we ran wires out the back, and the person who was wearing it in the video, if it was me or one of the other people, we had to carefully run the wires up our sleeve. And so if you go back and you look at all of the shots in the original Kickstarter video that had the watch actually powered on, a person was always wearing long sleeves because the wires had to go up their arm to a battery pack that was kind of attached to their arm. I don't actually know if I've told that story before. So, yeah, the first Kickstarter video definitely had some movie magic to it. All right, enough ancient history for now. Let's get back to the topic at hand. How do you build a smartwatch? What are the steps that are needed in order to build one? As I've mentioned before, I think on a past blog post, designing consumer electronics products is an exercise in constraint maximization. What do I mean by that? So first of all, when you're building a new product, you need to identify a target experience goal that you're aiming for. Like, I want to build a smartwatch with an always-on, daylight-readable screen that lasts for 30 days. That's your target goal. Then you need to break that down into features or specifications that your watch will have. These are things like an e-paper display, Bluetooth low energy, a specific water resistance, and the price. It's a very important kind of feature, and you need to target. So let's say $150. Then you take those features and specifications and you create a design with hardware and software components that seeks to maximize those values. It's very difficult to get every single specification that you want because every time you pick a new component or a new feature, you may be trading off one specification at the expense of another. More battery life, higher price. Less water resistance, lower price. And so you're always trying to balance that equation and maximize it to the best of your abilities. So after almost 20 years building consumer electronics, this process almost comes naturally to me. I can do it in my sleep, or as I'm walking around, I'll see a new product and in my mind start thinking about, what does the exploded view look like? How do the mechanical and electrical systems plug into each other? I'll estimate the manufacturing price and start thinking and imagining, how does the software work? And it's a bit of a blessing, but a curse as well, because I'm constantly thinking about it. You can break down watch hardware into 5 key systems. First, you've got the microcontroller chip. Usually this also includes the Bluetooth radio. Then you've got the display. That's front and center on any good smartwatch. The third system is sensors and outputs, like the tact switches that are inside, touch sensor, microphones, accelerometers, speakers, mics, that kind of thing. The fourth one is the other electronic components. This could be the chips, passive components, the PCB, battery. And the fifth subsystem is the mechanical structure, like the case, metal case, plastic case, the straps or bands, the charge cable, packaging, that kind of thing. Now, picking components for the 3 latter parts of this system is actually quite straightforward these days. Picking components for the latter 3 systems is actually quite straightforward these days. There's a ton of really good options available at various price points for sensors, batteries, straps, watch cases, mics, you name it. So constraint maximization is relatively easy for these things. And I'll probably wrap all of these together into one blog post later on. But the 2 most challenging decisions that you need to make when you're designing a smartwatch are selecting a microcontroller and a Bluetooth radio, which is what I'm going to cover today, and selecting a display, which is extremely difficult, and I'm going to cover that in a later post. So let's dive into how you'd pick a microcontroller for your smartwatch. So back during the OG Pebble era, we used an STM32F2 series microcontroller, also sometimes called an MCU. How did we pick that one? Well, it's kind of a funny story. So I was hanging out back in 2011 at the Hacker Dojo in Mountain View. This was a great hacker space, place that we could come and work on electronics, and they had a bunch of 3D printers and all kinds of stuff. But I would usually hang out in the electronics room, and one of my friends, Hugo, was there, and he could not stop raving about this relatively new MCU that he was using. At the time, I was working on Impulse, the first generation, and the Impulse used an LPC 2103. For some reason, I just can never forget these microcontroller names. And so the LPC 2103 had a whopping 8K of RAM. And so Hugo thought that this was terrible and we had to improve. And he knew that we should head up to upgrade to the STM32 series, which had 128K of RAM instead of 8K. And this was the only reason why I even heard about this chip in the first place, or ended up using it in the Pebble. And to be honest, this is like 100% typical for me. I think all of the major chip selections that I've ever made have come from friends raving about a particular chip. And I guess I have a pretty delightfully eccentric group of friends who over the years have turned me on to all kinds of interesting chips. So this is a big thank you to my friends Hugo, Trammell Hudson, TL from Pine 64, Peter Barrett, and many others who've texted me at all hours about chips and why they pick them. And that's been super helpful. And now I turn to Twitter and I look at Blue Sky and I try to find new chips through there. But at the end of the day, you need to have, if you're building something like this, you need to have a group of friends who are just as crazy as you and can help you learn about random interesting chips. An MCU is the heart of a smartwatch. Think of an MCU as a miniature computer. It contains the CPU, RAM, usually flash storage, I/O peripherals, and even radios, all on one single integrated circuit. The specs of the MCUs that we used over all of the different eras of Pebble are contained in this one helpful table that I use all the time. So I'm going to link to it in the show notes. You could check it out and see which are the different chips and MCUs that we used over the years. But I want to talk about why picking the right MCU is so important for designing a smartwatch. It all goes back to constraint maximization. The MCU sits at the focal point of the most constrained governing equations: software compatibility, power consumption, and cost. So on the software compatibility side, embedded software, which is the software that runs on the MCU and powers the watch, is much more fragmented and requirement specific than computer operating system software. This is because computers have tons of hard drive space, they've got tons of RAM, so there's really no need to kind of optimize things perfectly. Like for example, if you run Linux or BSD or Mac or whatever, the Linux kernel contains over 17,000 device drivers. PebbleOS, on the other hand, as embedded software, has to be effectively hard-coded for the specific MCU that you're using and the drivers, and have custom drivers written for all of the peripherals and sensors. Switching to a different MCU brand, like we started with ST and actually stuck with ST through the entire first era of Pebble, switching brands actually requires writing new peripheral drivers for I2C, SPI, DMA, that kind of stuff, and adopting a different SDK and sometimes even a different build system. These changes aren't necessarily risky. You could do them if you really wanted to, but they take time to implement and test. And so most people, when they pick an MCU, they actually stick with the same brand as they continue through various generations. PebbleOS uses a kernel called FreeRTOS. And another constraint is that some chips don't even support FreeRTOS. They require a different kernel like Zephyr. And so more recently, as we were designing the new watches, we looked at Nordic's chips, and we initially started designing with an NRF 5340, but we just could not figure out how to get it to work without using Zephyr. And the prospect of porting all of PebbleOS to Zephyr was too big of a lift for us to really consider at the time. For Core 2 Duo, we decided to use an NRF 52840 chip. This includes both the MCU as well as a Bluetooth radio, all in one package. It's an older chip, but we were very familiar with it, and we knew that we could port PebbleOS to it relatively quickly. We were initially thinking about using Nordic's soft device BLE stack, and the 52840 is the last device that supports the soft device. The 5340 requires using Zephyr in order to kind of integrate the Bluetooth stack into the system. So we were planning to use the soft device, but then thanks to the clever work of Liam, one of my past Pebble colleagues and an avid Rebel contributor, we switched to using an open source BLE stack called Nimble. And funnily enough, now that we've switched to this stack, we could have used the 5340 in the end. But at that point, it was too late. We had already started developing the watch. We were pretty far along with the schedule, and we didn't feel like it was just too risky to switch back to the 5340 at that stage. The NRF 52840 is powerful enough for the Core 2 Duo, but for the Core Time 2, we needed an MCU with more RAM and processing power. We would have really liked to stay with Nordic since we had just spent a ton of time porting PebbleOS to work with their SDK and all of their peripherals. But Nordic's roadmap in the BLE MCU space just didn't have much for us. We looked at the NRF 54L15, but it only has 256K of RAM, which wasn't enough. It also just recently went into mass production, so we didn't have any friends who were providing reviews or raving about it. They've also got a 54H series with 1 meg of RAM, but it doubles in price, and we didn't actually need a meg of RAM. We really wanted just 512. The other consideration that we were thinking about is the bigger color display on Core Time 2 uses a special interface for memory in pixel displays. During the Pebble era with Pebble Time, we used a dedicated FPGA to power and talk to these displays, but that was an extra chip and cost more money. So I was on the hunt for a new MCU. I looked at a variety of options from Apollo, BES, Dialog, but I just couldn't find anything that fit our needs exactly. It was actually pretty tough. I was like going in circles, trying to, talking to everyone, seeing if I could find a chip. One of the biggest stumbling blocks was the lack of an open source SDK. One chip from BES really looked pretty good, but we ran into problems as we were trying to test it. There was just no open source SDK, no example code. Everything was locked behind an NDA. That wasn't going to work for us because PebbleOS is open source, and so we needed an SDK that would have an open source option. Luckily, as I've seen time and time again with my MCU searches over the year, lightning struck. I randomly got an email from the CEO of a smaller Bluetooth chip company called SiFli. We exchanged a few emails over the span of probably a few hours, and it became immediately clear that the CEO of this company was just extraordinarily interested in getting his chips to power an open source smartwatch. I flew out to Shenzhen a few weeks later to meet with their CEO, and I think we really hit it off. Turns out SiFli chips are basically custom designed for smartwatches. They already power tens of millions of other RTOS-based smartwatches from brands like Redmi or Oppo, Noise. So we were in good company there. The smallest SiFli chip, the one that we're looking at using, or the one that we're going to be using, has 512K of SRAM, which is exactly what we were looking at, and 16 megs of PSRAM, which our operating system doesn't even really use yet, but we could actually use it in the future. And now the wheels are turning. Like, how could we use this PSRAM? It also has a dedicated MIP controller designed specifically for the screen that we're using in the QuickTime 2, which means that we could eliminate this extra FPGA chip. The board gets simpler, the software gets simpler, we save a bit of money. And best of all, I think, is the power consumption numbers. It's wild. I think we're looking at less than 50 microamps for the main Bluetooth controller in a connected mode. And the chip's only, I think it's less than $2. So it's basically perfect. They even have a couple different options with more SRAM if we really wanted to get to a meg or 2 megs in the future using the same SDK. Oh, and of course, the best of all is the open source SDK. Their SDK is open source. It's on GitHub. And SiFli is helping us a ton to port PebbleOS to their chips as well, and publishing all of the code open source on our GitHub. So there you have it. The chip for the QuickTime 2 is going to be an SiFli-SF32LB52J. I haven't got that memorized yet, but pretty soon it's going to be etched into my memory for sure. I actually had the chance to invite Jingming, who's the CEO of SiFli, here for a chat a few weeks ago, which we recorded, and I've got for you to enjoy. I'd love to learn more about how you started SiFli. Like what caused you and your co-founders to start a silicon company?
Yeah, me and my team, we used to work on in the cell phone business. So we work on the application processors for cell phones, 4G and 5G. But then, the cell phones, they are actually getting mature and not as exciting as before. So for that reason, we want to bring similar experience like the cell phones to any other things that's possible. And when we look around, there's not many chips that can serve that market. And so it's probably time to, jump off the ship of the cell phone and do something more fun.
I think what you've identified is like a different band of technological gadgets, right? You have computers that are up here and they use heavy powered, well, actually now they use almost mobile processors.
Right.
But cell phones use a different category of chipset than, say, an embedded device. What was the first chip that you ever used? Like, did you use a PIC or a basic stamp, or what was the first microcontroller?
8051.
8051?
Yes.
Okay. What did you build with an 8051?
Well, I don't exactly remember. That was when I was in college.
Okay.
And we were building some kind of counter or something like that. And, let me take it back. It's not an 8051. It's actually because I'm in the electrical engineering department, and we were actually building a small computer out of the discrete components. So like NAND, the NOR, and the inverters, using a breadboard.
So you did basic digital logic. You were building flip-flops and...
Yes.
Okay.
Yes, that was way before the integrated circuits. So we used the discrete components to put together a 4-bit, I think it's a 4-bit computer. Very, very simple. And
so now people are doing that in Minecraft. Have you seen that people are building like 4-bit, 8-bit computers in Minecraft?
I've seen that report before, but I haven't really tried it out.
They're doing what you did on the breadboard in a computer. Yeah. And then, okay, so you were building, I guess we're skipping around a bit, but where did you go to school?Here did you study engineering?
My college is Tsinghua University in Beijing, and I got my bachelor's and master's there, and I went to UCLA for my PhD.
And you were studying computer engineering, electrical engineering?
Electrical engineering.
Yeah. I had the chance to visit Tsinghua. It was beautiful, and it was also right in the middle of like a little bit of Silicon Valley. Like there were startups that were...
Right. Zhongguancun. Yeah.
Yeah. Was that happening around the time that you were going to school there as well?
Yes. A big fun was going to the component market. There was actually a big component market in Zhongguancun, and it was fun to look into those different components. At that time, all the components are imported from US and Europe, and it was fun. And also buying the optical discs, that was a lot of fun. You
mentioned that your wife's a chemical engineer and my wife's a chemistry scientist. Now, you were when you were at that lab, were you actually working on and getting down to the chemical layer of chips, like figuring out like doping and all of the.
Not at UCLA, but I
Okay.
actually did it in Tsinghua University. We had this summer practice. So we went to the workshop and did all the etching and stuff to build our own board. I think it's a charger. It's a battery charger. So you put your rechargeable battery inside and it will charge.
So you etched your own silicon at that stage?
It's not silicon,
Okay.
it's the PCB.
Okay.
We etched the PCB.
Cool.
Yeah.
Yeah, that's fun.
Yeah.
Now, one of the questions that I had that I was interested in asking is, how do you start a silicon company? For me, it just seems like such it's not something that I've done before. Like I've built gadgets, I know how to do PCBA design, I know how to do firmware, but I've always purchased chips from other people. It's never once crossed my mind of like, oh, I want to actually go and build this chip that I'm going to use. How did you start a silicon company? And maybe a broader question is like, how does one start a silicon company in the modern day in 2025?
Silicon companies are mostly technology companies. So just like that, you're not familiar with chips itself. We are not familiar with gadgets. That's our problem. I always work on the technology, but I don't see my technology at work. It's the same problem that I had when I was at school, undergraduate and the master's. Right? You learn a lot of technologies, a lot of theories, but then how do the theories turn into a real product? Be the product a silicon or the product be a real gadget? That is something I'm actually moving forward to closer and closer to the end market.
But you didn't. You started a company that's just making the chips. You're making the building blocks that other people build on top of, right?
Yes. We do the chips. We actually build the reference design as well. For example, we build a reference watch just to understand how the watch works. And then learn the experience, what the customers, our potential customers, will be like to have, to look into like the buttons and also of course, the power consumption and the display effect and also the hardware usability, right? So that is something we need to look into. We don't just do the math in the silicon. We need to understand the real product.
But take me back to the early days. Like, how many people, how big was your company when you started working on it? How much money did you need to raise in order to build the first prototype? How long did it take? Most people, I think a lot of people just don't have experience with this. This is kind of the dark magic that we've never been exposed to. So shed some light, share kind of the nitty gritty. How did you make this happen?
Well, that actually mostly comes out of the experience in the semiconductor industry. I've been working on this kind of semiconductor for more than 15 years. So I know how exactly it's being built from scratch. Then you need a lot of experienced engineers to help you. At the time that when we had the first prototype chip, working chip, we had about 25 engineers. So that takes a lot of people. But nowadays.
And what's the breakdown? So like, there's 25 people at the company. You're there. Your co-founders are there. Mm-hmm. Is it 25 engineers? Is it 25? Kind of walk me through what does the company look like at that stage?
Yeah, we had the chip itself is an SoC. So we had a combination from all different aspects. For example, there's a radio circuit designer. Then there's analog circuit designer to design the ADC and the pad. And then there's digital designer to design the PHY, so you can receive the signals from the microwave, right? And then there's digital design engineers to put the ARM processors together into an SoC. And then you do the backend, meaning you translate everything from a hardware description language to the real devices like transistors. And then you tape out. So that part takes like 15 engineers to do.
15 engineers to do all of that, the various stages that you described.
Yes.
Okay.
And then there's driver engineers, right? And then there's graphics engineers, application engineers for graphics. And then there's Bluetooth protocol stack engineers. So, 3 or 4 here.
It's a big company. It's a big startup. So like startups here, are in a garage and you could have pizza together. With 25 people, you had to have some serious office space for that.
Yes, we had a fairly big office there, and and we had to have a lot of servers running. So doing a silicon is much more complicated than before. At least much more complicated than when I was doing the etching at my college.
But you're a fabless company, so you will do the design and then work with someone
TSMC.
like TSMC
Yes.
to go and manufacture it. You worked for Marvell, correct?
Yes.
Before, but I'm sure that when you're working at a big company, you don't really get exposed to every single part of the process, right? You are an expert and you were working in a particular part of the stack, or you had a team that was doing it. But when you start your own company, like it's all you. Like there's no one else. Was there anything unexpected? Like what were any stories that you could share of those early days where you were thinking that you knew what you were doing, but then something happened and you were like, wow, this is unexpected?
Well, there's a lot of things that was not expected at the beginning. For example, we started with an SoC that uses the Bluetooth Low Energy as the connectivity. But later on, the market moved from BLE to a dual mode Bluetooth. That was not expected in the beginning.
So you were actually targeting BLE only initially?
Yes.
What was the product that you had? Like, was there a certain class of products that you had in mind when you were starting SiFli?
When we looked into this market, we saw Nordic and Dialog, all those companies behind the wearable gadgets, especially Dialog. It's inside the Mi Band, right? The Mi Band, it's pretty much the wearable in China at that point.
And that was BLE only, right?
Yes, BLE only. And I didn't realize a phone call feature is important for a phone, for a watch. So we thought that BLE connectivity is good enough.
Did you focus on watches exclusively at the beginning, or wristbands? Was that the primary thing that you were looking at?
We were expanding to other areas. Just that the watch is very typical AIoT device, meaning the AI kind of computing plus IoT connectivity. So we think once we have made a footprint in the watch business, then we should be able to expand easily into other markets. Yeah, that is our thought. It's we are using the wearable, especially the smartwatch, as the most typical AIoT device for the future and for the future kind of gadgets.
Was there, oftentimes when you start a company, there's usually one nugget of an idea or one insight that you had, or one thing that you want to push further than anyone else. Did you see something in the market that wasn't being worked on, or like one thing that you wanted to see exist?
Yes, that was actually a surprise finding when I was actually looking into this market. I talked to the CEO of a major wearable company. He was complaining about the computing power out of the Dialog chip. So the Dialog was running 96 megahertz M4 processor, and he was complaining that's far from enough. So I was actually curious. I asked him, how about I give you a 200 megahertz processor, which is double of what you're already having?
Yeah.
Is that enough? He said, he replied, no, that's not enough. So then I got interested in what's causing not enough kind of reply. Then when
you mean like what software does he want to run that's not currently being served by the Dialog chipsets?
Basically, he wants a bigger display. That's a clear trend.
Yeah.
And also there's
as you need more CPU to be able to drive the pixels.
Yes.
And
there's sensor algorithms that are becoming more complicated and also neural network based. So when you're talking about the neural network, then the existing computing power is far from enough. And then the similar thing for the graphics. When you talk about graphics, they pretty much use the CPU to do all the graphics. So that was the early stage of a feature phone. Then we could do that. We realized that the next thing is the power consumption. We need to cut the power consumption to be a much lower profile than the cell phone. That's exactly what we did for this company.
Interesting. So CPU, more power to be able to run algorithms and pump pixels out to the screen. GPU,
yes,
which hadn't really been done in the microcontroller class of processors, and then power.
Yeah.
Cool.
Actually, all these elements are already there in a cell phone silicon.
Yeah.
But
the power is not. The power is
at
much
a different
higher.
profile.
Yeah.
Right? And so for the AIoT devices that we foresee, when you need a fair amount of computing power, including graphics, including the AI type of computing power, and the regular CPU kind of power. On the other hand, then you need to have a much lower power consumption profile, so that the device can last for a much longer period with a small battery. That is something we see as a combination. So the two extreme, on one side, computing power.
People want it all.
Right, people want it all. That's why we started with this multi-core architecture, and that is actually directly borrowed from a mobile device, mobile CPU.
Having multiple cores, yeah.
Yes.
One of the things that, why don't we talk about how you and I met? So, we were kind of relaunching PebbleOS as an open source project a couple of months ago.
Yes.
And we were initially using Nordic chipsets, the NRF52840, and I think I had already published that. So it was on the blog that we were using Nordic. And then one day I checked my email and there was an email from Jingming. How did you get the idea to email me about this?
We're actually working on the open source community project since sometime last year, and I'm actually looking into all kinds of news, anything open source. But then again, I still realize I'm actually late to that PebbleOS open source news. So once I saw it and I read the news that you are relaunching the devices, that was actually a lot of fun and exactly what we are working on. So that's a perfect match.
It's rare. There's not too many chip companies that do open source SDKs. Why do you think that is?
Well, that's the post cell phone era that I'm foreseeing, because for all the AIoT devices, the thing can get fairly complicated. But again, they're not coming with high volume as cell phones. For the higher volume devices, you can invest a lot of R&D into the device, so you don't really need an open source SDK. You have plenty of engineers.
You're saying like the companies that use the chip have a lot of people, have a lot of engineers, so they don't need the open source kind of community.
Right.
But you're targeting products that aren't doing that are...
Yeah, so I haven't seen any new gadgets that can be compared to a cell phone in volume and in the market value, right? And in that sense, I see people like their own choices. For example, a smartwatch. I haven't had my favorite smartwatch yet.
What's your favorite smartwatch? What's your dream smartwatch look like?
Firstly, it has to be extremely low power.
Okay.
It's better to be a solar powered. So
solar powered.
You
okay,
never
cool.
have to recharge it. That would be my first choice. Right?
Okay.
And the second, I want to have a fairly big display, so that I can see it, because I'm in my 50s. I need to have a big display to see it.
It's funny, yeah. Like the first Pebble I put together when I was 22, it needs a bigger screen now.
Yeah.
Okay. Long battery life, ideally solar powered, bigger screen. What else? What is
a very sleek look.
Okay.
That is very personal, because I'm a tech guy. I need to have something that looks techy, right? And there's probably many people like me who are looking for that kind of gadgets. And maybe there's also female users. That's an underserved market from the smartwatch perspective.
But now you're thinking as a business. I want you to think as a person, just as Jingming, because there's a difference between what you think is a good product that's going to sell a lot and what's a product that you want to put on your wrist.
Yeah, the thing is, I think there's many people like me who haven't found their favorite gadgets yet. So it's probably not in a very high volume. Like maybe you have 20K enough, maximum to serve that market. How do we help them? That is help me is to help other people. That's exactly the reason why I'm looking to the open source way. Maybe we can come up with a new generation of software, like PebbleOS we're talking about, as the Linux for AIoT devices. That is something I'm looking for.
What are the open source projects that you are looking towards as good examples, like things that you and your company will emulate? Are there some companies or some chips or some SDKs that you prefer or think are doing a good job?
Yes, there was one point when I was doing the research on smartwatches. I saw this watch, Watchy. Yeah, That's
by SQFMI.
Yes.
Yeah.
And that was a very interesting device. Unfortunately, it's not really a low power consumption one, which is my number one.
Because it uses an ESP32. Yes.
But on the other hand, ESP32 has done a good job to enable the open source community. That's also the reason why, for smartwatch, even though the ESP32 is not a perfect match, people can still use it, can make it happen.
Yeah, I don't know exactly how SQFMI chose ESP32, but I imagine that part of it was because the SDKs are public, there's no NDA that you have to sign, and there's a lot of good examples on GitHub.
Exactly.
Yeah.
And there was some customers complaining in front of me about the original NDA stuff that we had like 5 years back. And they were frustrated because, in our NDA, there was a penalty if,
Yeah.
It's,
well, that's any NDA, any contract has that.
They didn't like it.
So you decided, so your current SDK has no NDA, you can just download it?
No NDA, it's already on GitHub, publicly on GitHub.
Yeah, and that was one of the reasons why, after you emailed me and we started chatting more, one of the reasons why we decided to pick SiFli for the new set of watches, because you were publicly kind of stating that you wanted to be part of this community, which is great. Let me take you back. One question I like to ask is, what's a gadget that had an impact on you? Maybe an early gadget that you owned, or one that you really wanted to own but you never got to buy. What do you remember?
It can take me a full day to talk about it.
Good, I want to hear it.
It's actually a Trio 650.
Okay, so it's exactly the Trio 650.
Yes, I had one of those.
We'll put a picture up. Okay.
That was in 2004 when I first got it. That was a big excitement because I was gonna get my PhD degree in the end of 2004. So I bought it as a gift for myself. That was a major fun for me. And
did you have a Palm Pilot before that?
No.
Okay.
It was actually too expensive for a PhD student.
So you had a cell phone before.
A basic cell phone. Yes.
Okay, so this was a pretty big upgrade if you're upgrading from a cell phone to your first Palm Pilot PDA.
Right,
okay.
Right.
And what did you like about the 650?
First of all, it's a color screen.
Yeah.
Color display. That is very good. I like it. The second, it's I can hack into it. That is a lot of fun. I actually installed a dictionary app in the device because I'm an international student. Sometimes I run into new words, right? So I learn from that dictionary a lot. And then I actually installed a GPS navigation app. I think it was a hack from the internet. I don't remember. It's probably TomTom or.
Yeah, back then, 2004, it would have been TomTom. Yeah, exactly.
Yeah, and that helped a lot because in those days when we go for a road trip, we actually print the Google Maps, not Google Maps. It was Yahoo Maps.
Yeah,
yes,
exactly.
Yahoo Maps, and then we put all the.
So the Trio had a GPS chip in it?
It doesn't. So I actually bought a GPS receiver with Bluetooth connectivity.
Okay.
So we connect the Bluetooth device to the GPS device to our.
Did it have Wi-Fi as well?
No.
Okay.
No Wi-Fi.
Have you ever gone war driving? Do you remember that? Where people would drive around to find open Wi-Fi networks?
Yes, I think I've seen one before.
I wonder if the Trio could do that.
Wi-Fi was actually a new thing during my PhD period. My PhD was about Wi-Fi.
Okay.
It's the 8x8 Wi-Fi, 8 antenna Wi-Fi.
MIMO?
MIMO, yeah. You don't see it very often still in the consumer markets, but then in the commercial markets, you see there's 8x8.
Interesting. Cool. Last question. So I wanted to learn from you, where do you see, so we were talking about these different layers, right? Like the computer layer, the laptop layer, the cell phone layer, and then the microcontroller embedded layer. Mm-hmm. Where do you see that layer going over the next few years? Are there new technologies that you think are going to start appearing on this layer? Or what's next? Like, where do you see MCUs, embedded radios in the next 3 to 5 years?
First of all, I think the MCUs is going through a major upgrade because of all the connectivity. So we call it AIoT or sometimes MCU plus. So it's a connected MCUs. Then it's a game changer. It's like changing the game in the cell phone business. It's changing the business of MCU as well.
To add radios, to add connectivity.
Right. And second, it's the tool chain. Because, before we were programming like C, C++ at most. Nowadays, people are programming using Python or JavaScript. That makes the programming a lot more easier and quicker. So we need to have the tool chain prepared for that kind of change. The second is the silicon itself, because Python and Java programming needs a lot of computing power and much more memory. That's why, for all of our chips, they are equipped with a much higher memory capacity. So you don't have to worry about the memory constrained by those like 32K, 256K SRAM.
So what are we going to see on chip? Right now, your chips go up to 32 megs of PSRAM.
Up to 64.
64. Meg. So what are we going to see? Are we going to see like a?
We are thinking about
a gig. No.
AI models running on the MCU.
Okay.
Yeah.
And so, but where does there must be some, as you graph the power consumption of an MCU against the capability, there must be some point where the trade-off is such that you may go to an ARM8 or like to a higher power.
That is possible.
MCU. Is there like a certain will the kind of phone level microprocessors, will they come down in price and power consumption to meet MCUs, or how will that work?
The biggest power consumption of the application processors is actually the operating system. It's the Linux, because the Linux is requiring that much of footprint and a lot of data throughput. So that is something that you cannot really change. But again, if we can come up with a much more powerful RTOS system, and it solves your power consumption problem, and it solves the hardware cost problem, that actually make life a lot easier for the IoT devices.
Sorry, my eyes are just watering too much. Too
It's
much light.
Too bright. Yeah.
I haven't done that before. Sorry. I'm not in tears from your not crying about the future.
You see, your life is harder because it's.
I know. I've got a few more.
Eyes.
Yeah. Cool. This was one last one. If I could ask one more question, what's the cleverest hack that you've seen someone do in the embedded world? Like, when you hear about someone using a chip in a very interesting way, or someone doing something with software. Do you have anything off the top of your head that you remember about someone doing something kind of like a crazy hack?
Yes, there's two things that I can come up with. The first thing is with our own engineers. We had this AI engine in our chip. So it's basically an accelerator, hardware accelerator for the matrix computation and convolution. There's a math called convolution. And at some point, there's a customer talking to us about the Gaussian effect, Gaussian blur, which we see on the iPhones and Apple Watches. And they were asking us if this is doable.
Is it hardware accelerated, or?
It is hardware accelerated, but never before on a smartwatch.
Okay.
So I told that idea to our engineers. And the two of our engineers, one is a hardware engineer, the other is a software engineer. They came up with this idea that we can probably use our AI accelerator to do this Gaussian blur.
But your AI accelerator, is that running on the GPU, or?
It's separate from the GPU.
It's an NPU,
yeah,
okay.
Yeah. So I didn't realize this kind of AI accelerator can be used for graphics. That was a major surprise to me. And they did a very good job, because actually basically the fundamental math is very similar. It's always matrix convolution. So that's why they actually.
So did they train a model to do Gaussian blurs, or?
No, they didn't do that.
Okay.
It's just a plain filtering.
Okay.
Yeah, that's one thing.
Cool. That's a nice hack.
Yeah. The other surprise is actually happening in our current open source community. There's one developer. His name is his web name is Simon.
Yeah.
He actually ported the Unix to our memory controller, which is a total surprise. and he was actually running a game from the 90s on that Unix. That was fun. Maybe I can show you.
That's pretty cool.
Yeah.
Okay. So that's people in your like on your GitHub posting interesting hacks that they're doing with SiFli.
It's not exactly GitHub. It's actually a QQ group.
QQ group. Okay.
Yeah, we have a big, like 300 something engineer QQ group.
Nice.
And they were actually posting their fun stuff in the group.
Well, in my past life, I did a lot of chat interconnectivity. Maybe we need to build a QQ to GitHub bridge so people can see on both sides
Yeah.
what's happening.
Yeah, we actually just did a bridge between the GitHub and the Git because there was a glitch a few days ago on GitHub. They blocked all the IPs from China and Hong Kong.
Really? Okay.
Yeah.
Oh, yeah, I think I remember seeing that. Yeah. So you now have to build that bridge so people can communicate on both sides. Yeah. Very cool. Cool. Well, thank you very much for the chat, Jingming.
Thank you, Eric. Thank you for having me.
Well, thank you, Jingming, for being the first guest on my podcast. And thank you, everyone, for joining me on another episode of TikTok with Eric Michikowski. We'll see you soon.